Alright, here we are on trigonometric ratios. This is unit 4.3. Correction on that, it should be section 4.3. And today we're going to start exploring what can we do in situations where we want to know the coordinates of a point on the circle or to gather other information about the triangles on the circle. As you'll recall, we've been using 4.1 and 4.2 to get a better understanding of what the unit circle is, and today we're going to mix in the trigonometry we've done in previous years to get a little more information about this unit circle. So, as you can see here, and I should make a note today that while I'm working, whichever of the two windows I'm on, you should get this nice highlighted section. It'll help keep track of where I'm working. So today we're taking a look at a unit circle like this down here. So we're saying if I had some kind of a triangle, such as they're showing here in blue, then there is a circle that could be drawn of unit 1 to work out this triangle. So the way they've drawn this here, this might be where the actual arm of this triangle from O to Q is, say, 1.3. And using a unit 1 circle, we can figure out something about these triangles. We could use similarities in triangles to figure information out from the circle and extrapolate that to triangle OQB. Now, we're not going to be doing that today, but that's just sort of a, here's what we sort of do with these things. So before we get too far focused on this, I'd like to show you a couple of graphs on what's going on here. So let me just back this up. So here we have a unit circle, and we're going to be watching this arm, that blue dot specifically, as it travels around this circle. And as it travels around the circle, we're going to be plotting the outcoming graph here. So let's take a look. So I'm going to pause it here for a sec. So note, this blue arm here matches this blue arm here. So what they're saying is as this height increases, this is increasing. So I just missed it. But when it was sitting on 1 here, you were at a height of 1 over here. And one other thing to take note is that while this is at 1, note that down here, that's not at 1. Right? So this coordinate would have been 1, this would have been 1.3, 1. Because as you'll note, this red arm here, which we'll recall as the arc from previous classes, is what's being plotted along the x-axis here. That's how they're doing this graph. So as this blue arm moves out, it's going to generate a sine function for us. So you'll see when it went negative, the graph goes negative, and when it gets back here, it goes positive. And if you were to continue, if you did another lap around, it would just make the same function. And it's just continuous. So it'll go as long as you want, because as long as you keep going around, you can just keep graphing here. And as you know, if you went in the opposite direction, if you went the clockwise direction, you can make the negative side of this sine graph. So that's the sine function. Alright, so had a few technical difficulties, but we should be back up and running. Unfortunately, the nice little blue outline won't be following us today. So we are discussing the connection between the circle and trigonometric functions. So in order to understand what these different functions are, we need to know how the different coordinates link to what the system would be. So let's start by drawing a triangle. So here we have a standard triangle, and what we've known so far, this angle in here we call theta, and this arm that would be sitting out here is a distance of radius r, which if you're working with the unit circle is 1, and we call this point P. So now if this is a theta angle that we're looking at, this arm here, which would be on the y, we call the opposite. So that's the opposite. And then this one here is going to be the adjacent. So for this given triangle that I've just drawn, if I wanted to determine sine, So sine is going to be equal to opposite over the hypotenuse, opposite over hypotenuse, which on the triangle I've drawn, this is our y coordinate, right? So whatever this is, whatever point P would be, x comma y, the height of this line is whatever our y coordinate is. So opposite becomes y, and the hypotenuse is radius r. Now, if we're dealing with this, we're going to have y over, and if I have a unit circle, radius is 1. Let's write that here. Radius is equal to 1. So that's y over 1. Therefore, sine ends up equaling y. Actually, this should be sine theta. Forgot about that. Sorry, guys. That's sine theta. That should be in there. So sine theta equals y, whatever this height here would be. Let's take a look at cos. Let's do cos in a different color. So cos theta is going to be equal to, this time, adjacent over hypotenuse. These are just the SOHCAHTOA rules that we've learned in previous years. And if not, here's a little reminder for us. So cos theta will wind up being, now here adjacent, what's the length of this arm? Well, the length of this arm is whatever x coordinate is, because we went this distance on x before we went up. So adjacent becomes x, and again, hypotenuse is still r, and when we calculate this, cos theta will wind up being x over 1. Remember that our radius for a unit circle is 1, so this means that cos theta equals x. Now, the last trigonometric function we need to know, or the last of the primary three, is tan. So tan theta is equal to opposite over adjacent, which, in what we've been looking at here, opposite is y and adjacent is x. So tan theta is equal to y over x. So these are the three trigonometric functions that we will need to know. Now, there are three other trigonometric functions, which you may or may not have seen in earlier math classes, that you will need to run into here. So let's take a quick look at what those would be. So the first one would be, alrighty, so we know the three trigonometric functions that we need. They were just on the screen. I would have had that, so we'll cut this portion too. So the other three trigonometric functions that we're going to need to know are, one's called secant theta, cosecant theta, and cotangent theta. Now, all these is something called a reciprocal. Okay, all of these are simply reciprocals of the function, and remember that a reciprocal is simply 1 over x. So for the first one, secant theta is equal to 1 over sine. Cosecant theta is equal to 1 over cos theta, and cotangent theta is simply equal to 1 over tan theta. So let's do this in red quickly. So if sine theta is, we've determined just y over the radius, then secant theta is going to be radius over y. So radius over y will give it to you for any of the units, any circle that you're working with. So if it's a radius of 2, it's going to be 2 divided by the y value. If it's 3, it's just going to be 3 divided by the y value. In this unit circle system that we're working with above, this is just going to be 1 over y. And same thing here, is if we're looking at cos, and cos is equal to x over r, then 1 over cos theta, or cosecant, is simply r over x, or 1 over x. And I'll clean these up in a moment for you. Now, the last thing here, tan theta, remember that tan theta we said was x over y. So cotangent, or 1 over tan, would just flip this, and this is going to be 1 over x. So let's clean this up so it's a little bit easier to read. So let's take a look at, so we said the first one was secant theta, which is equal to 1 over sine theta, which is going to be 1 over y. Cosecant theta is just going to be 1 over cos, and that one would be 1 over x, and then finally cotangent theta is equal to 1 over tan theta, which is the flipped version of tan, which is just going to be y over x. So these are the identities that we need to know when we're working on these problems. So what we'll do is, in class, I'll hand you some homework. I might even throw it up on the web, and you'll need to know how to apply these things. So in the next bit of this video, what I'm going to do is take a look at 2 types of examples, where I'll show you what you can do trying to figure out these equations. And then what I'll do is probably make some videos of me walking through different examples, which you can look at in your own time or when you want to, or just leave them if you can solve them without having to see some more examples. We are going to now work on an example of determining exact values for trigonometric functions. And I want to get cos of 5 pi over 6. This is the first example that I'm working on right here. So A, they're walking us through an explanation here. So let's walk through this one together to get an understanding of what's going on. So 5 pi over 6, how can I figure out what that is? Well, if I'm working with pi, in terms of pi, 6 pi over 6 would be the same as saying pi, right? So this whole angle is pi, so I can express that in terms of 6 pi over 6, because 6 over 6 just reduces to 1. Now if I minus 5 pi over 6, I'll be left with just pi over 6. So remember, 6 pi minus 5 pi, I don't write it here, but this means 1 pi over 6. So that's how I got it. So let's draw this on here. So, okay. So this here is 5 pi over 6, which means that when I'm looking at a triangle, that was a bad one, this is pi over 6 in here. Okay? And the reason I'm doing this is I can't figure out 5 pi over 6.